Okay, so I think we can start and then people will come on in later. So, good afternoon, everybody. I'm very happy to present the speakers of today, qmeets, and those are Alioscia Hamma and Salvatore Oliviero. And the former is a professor of theoretical physics at University of Federico II in Naples. He has been around the world, Boston, Tsinghua University, Perimeter Institute, and now he's back in his hometown. And his main research activities are quantum mechanics and quantum information. But recently, he's been at the forefront for studying quantum magic, magic in many body systems, quantum chaos. He's interested in black hole physics, quantum algorithms, and so on. Then the second speaker is Salvatore Oliviero. Now he's a postdoc at Scuola Superiore Normale di Pisa in Italy, and he's a former student of Professor Hamma, and now he's working on quantum magic as well as quantum algorithms, quantum information, bosonic state, continuous variables, and so on and so forth. So I think they will explain to you what they are interested nowadays, and I think with this we can start. So please.
Okay, can you hear me?
Yes.
So Daniele, thanks for the nice introduction, and I want to thank the whole team of qmeets for inviting me to give this brief talk about magic. And so can you remind me how long I have?
You have almost half an hour, like 20
Good.
minutes plus
All right, good.
10 minutes questions and so on.
Okay, so I understand that in this audience, you are all, very versed in quantum physics and research in quantum physics. And I think that many of you have already heard talking about magic. It is one topic that it is fairly very well followed nowadays. And this talk, I will try basically to convey two ideas. One is what is magic, and two is why you should care about that. And I think that this second part is really warranted, and the answer is not just, oh, well, because there is a lot of attention on it, and there are many papers being published on that. You will see. I will come onto this theme over and over during these few minutes. Okay, I think that one needs to make the case why you should care, and this implicitly also tells you when and why you shouldn't really care about it. Okay, let me get this started. And okay, so in this slide, I'll try to say, okay, what is really quantum mechanics? And many of us start learning quantum mechanics thanks to a demonstration or a schematization of the Stern-Gerlach experiment. We all know there are silver atoms that are collimated and go through a non-uniform magnetic field. And then, instead of being all over the place, they show two discrete values of some quantity that reacts to the magnetic field that one calls a spin. And we know that, okay, so this is interesting, but what quantum mechanics really tells us is that if you rotate these magnets and you use sequential measurements, so you first measure this spin in the z-axis, then in the x-axis, and then again in the z-axis. Although you previously had determined that in the z-axis the value was +1, when you measure it again, it's completely undetermined. And here, Werner Heisenberg reminds us that, okay, at the essence of quantum mechanics is the fact that there are physical properties that are incompatible. So, having determined one of them perfectly gives you maximal possible indeterminacy on the other one. Okay, so we know this is at the heart of quantum mechanics. And what is magic? Magic is actually something slightly weaker of this incompatibility, and it's just partial incompatibility. Okay, so imagine that instead of measuring here along the x-axis, I would measure along an axis that is in between the z and x-axis. Well, now you would have that knowing something about this new measurement actually has some correlation with the value of z. Okay, so you have some information. You don't have perfect information because there is incompatibility, but it's not the maximal possible incompatibility. Okay, so it is just less of the very important feature of quantum mechanics. And this is one reason why for a very long time this property has been neglected, because if at the heart of quantum mechanics there is incompatibility, you just want to have as much as incompatibility as you can to have the strongest possible quantum mechanical effect. And well, so the other thing is the following, that if you have incompatibility means you can have superpositions, and once you have superposition and many states, so composite systems, well, these two things together almost invariably give you entanglement. Entanglement is everywhere in quantum mechanics. And by the way, you should ask the same question, why do we care about entanglement in quantum mechanics? Because all states basically are entangled. The non-entangled states are very rare. And for 20 years, people, our community has published thousands of papers saying, oh, look at this system, it has entanglement. Well, of course it has entanglement. Entanglement is everywhere. This is not the right reason to care about that. Okay, so you need to know why you care about entanglement, what type of entanglement, what is telling you, when it's surprising that it's there, when does something interesting, not something that is always there. Okay, so here I'm showing an example of entangled states that are a bell pair. Notice that to prepare a bell pair starting from 0, 0, oops, you just need the Hadamard gate and a control knot. And of course, entanglement between two subsystems measured by the Renyi entropies associated to the reduced density operator. And please, I would be very happy if you feel free to interrupt me anytime you want during the talk to ask me questions. You don't need to wait until the end. Okay. And now, okay, so people say, look, entanglement is the defining characteristic of quantum mechanics. That's all I need to have quantum advantage, quantum complexity, interesting, spooky behavior of quantum mechanics. So let's start with the very first thing that we would believe, oh, look, this is something really quantum mechanical. And, well, I have it because of entanglement, and it is Bell inequalities, right? We know the Bell inequalities are a landmark of mechanics, and I will show them in the form of the CH-SH inequalities and the rules that we have some Bell operator, and the rule for forming this Bell operator is that this is going to be made of, it is actually 4 measurements, and each of these must be made of local operators. And because we need incompatibility, well, let's choose them, either compatible or maximally incompatible. So we pick this as a choice of Bell operator. So you have sigma x on Alice and Bob, sigma x and sigma z, z and x, z and z. So you can see that these operators may show maximal incompatibility because you have x and z, and they must be local, right? Otherwise, if you would start choosing operators that are no local between Alice and Bob, so they're not the tensor product, then you may be able to violate Bell inequalities even with the product state. But you are cheating, right? You are putting the entanglement in the operator. And you also know that you need incompatibility. You know that if you only put all z, nothing will happen. Okay, so you need to use x and z. Okay, so this is our Bell operator. And this operator has as operator norm 2 square root of 2. And this tells you, okay, so there must be a quantum state on which this operator assumes this value, right? Is the eigenstate of maximal eigenvalue. And this state, psi, is not phi plus. It is phi plus in which you rotate the first qubit along the y-axis by pi over 4. In fact, if you only use phi plus, you don't violate Bell inequalities. Okay? So you need this operation. You need this R. Well, notice that one thing that I could do is that instead of measuring in this state, I could measure in phi plus. But then the operator that I'm measuring is RBR. Right? It is, I'm just taking the passive point of view. So I'm keeping the state fixed, and now I rotate my operator. But now this operator is not the sum of local maximal incompatible operators. They're still local, but they are not maximally incompatible. So in other words, if you only use entanglement and maximal incompatibility, you do not violate the Bell inequalities. You must have less than maximal incompatibility, which is what I call magic. Okay, so the very first thing that is, what is the most elementary thing that really sets apart quantum mechanics from the rest? We know, it's entanglement, but entanglement is not enough. You need both entanglement and magic. So that's the first reason why you should care about magic. And in fact, this actually can be quantified. And the way we do that is that, okay, we have this protocol, we initialize our state, something that is all zeros, then we have operations, and then we have measurements. And so our initial state should be as neutral as possible. And then we have this operator, that is the Bell operator, that doesn't contain entanglement. It's factorized and doesn't contain magic because they're maximally incompatible operators. And now this is your expectation value. And you can prove that if these operations are either factorized or not able to inject magic, that right now we say, they're Clifford operations, then the expectation value of your Bell operator is upper bounded by 2, so you don't violate CHSH. And in fact, if you try to plot the probability of violations against something that is quantifying at the same time entanglement and magic, then you have something like this. Okay, so this is the first message. You need this weird thing called magic to violate Bell inequalities. Okay, and here, so now let's try to be slightly bit formal and understand what it means to not be able to inject magic, which means belonging to this CL, which is the Clifford group. And, well, this is the formal definition. The Clifford group is a subgroup of the unitary group, and it is the centralizer of the polygroup, which just means that takes a tensor product of poly operators and brings it in another tensor product of poly operators. The generators of this group are H, CX, and S. Okay? So if you only have access to these operations, you generate all Clifford group. And the question is, oh, what do I need to generate everything, the whole unitary group? Well, you need very little more. You just need a slightly more powerful operation, which is the square root of S. Of course, if you have the square root of S, which is this unitary operator, then you can also do S because you just apply square root of S twice. Okay. Now if you have this, you generate everything. So this very little difference is the difference between the Clifford group, which is a proper subgroup of the unitary group, and the unitary group. And so without, if you only have access to the Clifford group, you don't violate Bell inequalities. You need to have access to resources outside the Clifford group. And this is what we mean by saying, oh, you need to have access to magic. And okay, so this is an example of a quantum circuit, which is made of all these unitary operations. And okay, so these are some examples. This looks very complex. Now, we would like to quantify how much of these non-Clifford operations that in this circuits are only these two gates here, one is using. And now you see, this is a problem that is very akin to the problem of quantifying entanglement. And the way to quantify entanglement would be, okay, let's take the set of all the states that are not entangled, all the product states. So a measure of entanglement for one state is the minimum distance of this state from the set of non-entangled states. You understand that this minimization is a very daunting task. It is basically uncomputable. So we would be able to define entanglement in a very precise way, but we will not be able to compute it, forget measuring it. Okay, so luckily we have the von Neumann entropy. The von Neumann entropy is probably the unique quantifier of this distance for pure states. Okay, good. So that's why we can publish many, many papers about entanglement, because we can compute it. Now, for magic, you could do the same, okay? You take all the states that I can generate by just Clifford operations. This set is called stabilizer states. Then magic of a state is the distance of the state from the set of stabilizer states. Good. Yeah, this is a great definition, mathematically very sound, uncomputable. So what you need to make, to compute this resource, which is important, is to have the entropy, the von Neumann entropy for this quantity. And this is the so-called stabilizer entropy. And this was defined, and most of its properties were published in this paper, where Salvatore, who is the speaker that will speak after me, and Lorenzo Leone, at the time my students, and I, we defined this thing, which is actually a very simple thing. I will explain in a second. Subsequently, Lorenzo Leone proved that it is a monotone for any kind of Clifford, even conditional Clifford operations on pure states. Okay, so this is something very easy. So you know that for every state psi, the Pauli operators are a basis. They're just a basis. If you think of one qubit, this is the block sphere. For many qubits, you have Pauli strings. When you do tomography, this is what you do. Now, to the expectation value of this Pauli string in this state, you can associate, which is the trace of p psi, you can associate a probability, which is the square of it and not properly normalized. And now this is a probability distribution. It has a very precise operational value, which I will not discuss right now, but it is a probability distribution, and you can compute the entropy of this probability distribution. So it is telling really how these basis elements are represented in psi. How well, right? If you have a lot of entropy, it means okay, most of them are represented equally. If only few of them, or only few, there are always many, but marginally, relatively few, this means that you have less entropy. Okay, so this is just the formula of this entropy. Being an entropy is computable, just like the von Neumann entropy. And like I said, it's a unique computable monotone for pure states. If you have mixed states, now you have to subtract the Turani entropy, and it's still a measure of something. What this something is an exciting rich quantity. I will not talk about it right now for mixed states because it would take us too far, but let me just say it is not just magic. In fact, it is a richer, more interesting thing. Okay. So this is the stabilizer entropy. This can be measured, and we did it again. Lorenzo and Salvatore and Seth Lloyd are on this paper where the quantity was measured using the randomized measurement toolbox, and this was made on IBM quantum computer. So it's not only something that you can compute. By the way, now there are numerical methods to compute it efficiently based on Pauli sampling, but you can also measure it in the lab. Okay. Now, how long do I have? How much I've spent for my 30 minutes?
10 minutes almost.
Okay,
maybe
I have 10 minutes.
Yes.
All right.
So,
okay. So now I will have to speed up a little. I hope that what I did so far was very comprehensible. And I want to tell you why you should or shouldn't care about it. Okay. And one thing should be clear, that it's very easy for a state to have magic, because even if you have one qubit precessing in a magnetic field, as long as it's not pointing on the z direction or in the x direction or in the y direction, the axis of maximal incompatibility, it will have some magic. Okay, so it is an extremely common thing. If you only write a paper saying, hey, look, I studied this system, there is magic. It is really like saying, hey, look, I studied this quantum many-body system, there is entanglement. Okay, it's there, of course, it's there. What is important is to understand what type of entanglement, what type of magic, and what is telling me. And the main reason is that this is the ingredient you need to understand quantum complexity. Okay, so we don't really know what it means, quantum complexity. but we feel it's very important. There are many approaches, and one approach, which is the most common one, is to say, look, I have some elementary operations that are my gates. And now to go from one state A to which is my reference state, to a state B or to a state C, I find the path where I minimize the number of operations, the minimum circuit length. Okay, imagine this is the minimum circuit length for C, this is the minimum circuit length for B, while C is more complex than B because I need more operations. Okay, this is one point of view. There are other points of view, which is, fix the number of operations. I use n square operations, n is the number of qubits. And there are some patterns that are simpler, some patterns that are, look very complicated. And the reason why they're more complicated or less complicated is because they are very similar to many others. And this is the Boltzmann idea that says, look, even if I take something that happens in a very short time, if around it there are many equivalent states, so they're different, there are many micro configurations, but they're all equivalent, well, then this is something complex. But if there are only a few around that, well, then there is something simple. So this is the point of view that we would like to take. And I want to show you what are the ingredients to make something complex. And the ingredients are entanglement and magic at the same time. And why at the same time? Because we know that if there is low entanglement, everything is can be simulated very efficiently on a classical computer. So it's simple, by MPS, no matter how magic you put in it. On the other hand, if you have a low magic, and no matter how much entanglement you have, you are in the region where you can use the stabilizer formalism, where there is an efficient representation of quantum computation and quantum states. This is also efficiently simulable on a quantum computer. So low magic and low entanglement is this green area. This is all not complex. And what you don't know what to do, the dragons are here, is when you have both magic and entanglement. And one paradigm that one could study is the so-called paradigm, of T-doped Clifford circuits, in which you saturate entanglement and you slowly inject magic. And so you look at this part of the phase diagram. There are many open questions in the relationship between magic and entanglement. For instance, you cannot cram as much magic as possible in lowly entangled state. So this region is empty. In order to make room for more magic, you need to increase the entanglement. If you want a difficult problem, is find the shape of this curve. Nobody knows. It's challenging. It's very interesting. This is the paradigm of T-doped Clifford circuit. Because I'm running out of time, I will not explain why this entanglement complexity tells us a lot of stuff about quantum many-body states and distinguishes many-body localization, ATH, random methods theory, and integrable models. I want to tell you that the important thing is when you pair in the proper way entanglement and magic, you have the so-called non-local stabilizer entropy, which is, I have to skip this, it is defined in this way. So you take a state psi, and the non-local part of its stabilizer entropy is what is left after you erase unitarily all the possible magic locally. Okay, now this is not trivial. Not every state has it. Okay, so this is the non-local part of the stabilizer entropy. And so this is not trivial. This is measuring at the same time entanglement and magic. It is 0 when you have low entanglement or low magic. And one reason why it is useful is because it has to do with the holographic dual gravity. In AdS-CFT, one of the major successes of the holographic correspondence is that if you take AdS and you take a region A and you find the surface that is bounded by A, the surface of minimum area, this minimum area is actually the entanglement between A and B in CFT. It's great. This is a great success of AdS-CFT correspondence, is making the correspondence between a geometrical object, which is the area, the measure of a surface, to something that is quantum mechanical, that is entanglement. Notice that geometrical properties are one part of general relativity. Okay, it's telling you, oh, you know, the geometry is such and such, and being the geometry such and such tells you how particles move, right? They follow the geodesics. But general relativity is bad as a counterpart, right? Is that the fields, the matter, the particles back react on geometry and change it. And now you ask, what is the holographic dual of this, of the back reaction? Okay, and this is called brain tension. Is actually what you insert is that you insert a cosmic brain which bears an index n, because instead of being measured by entanglement, it's being measured by higher moments of the Rayleigh entropy and the susceptibility to this index. So this brain tension is back reaction, okay? Or at least it's the back reaction due to the insertion of a cosmic brain. And this was found by Dong in a very beautiful paper. And now, okay, so what does it mean, CFT? Well, really nobody knows, but we proved in this paper that we have this theorem, the back reaction is actually the non-local part of magic in CFT. So this is what it is. Okay, so this is the back reaction. And that's why when you combine magic and entanglement, you really get something non-trivial and interesting. And with this, I can finish, and I will spend just 2 words, and then I will take questions to introduce Salvatore's talk. Another very remarkable way of using how magic spreads in a many-body quantum system is the fact that this stabilizer entropy can be manipulated and moved around, and this can be used to do something that seems impossible, which is to decode Hawking radiation. And how to do that is actually the talk of Salvatore, and I'm looking forward to hearing it as well. Okay, so I think I'm done, and I'll take questions. Thank you very much.
So, is there any question? Thank you for the nice talk, by the way. Is there any question for Professor Hamma?
I have many actually, if I may just start.
Yes, of course. Go ahead.
Thanks a lot for a nice talk. I have quite some general questions because I basically don't know anything on stabilizer entropies and so on. The first is, you said a couple of times that stabilizer entropies are monotonic. I suspect that you mean something like that they're non-increasing under stabilizer operations or something like this. Is this correct?
Correct. They're monotones. So they are not increasing under Clifford operations, yes. Operations that preserve the set of stabilizer states.
Is this an obvious result? Because just from looking at this definition, this is not clear to me at all. Like when you look at the Rényi entropy for arbitrary alpha, this is not clear to me at all why this should be true. Is there an intuition for this?
Okay. Yeah. So sorry, I understand question. I understand the question is whether it is obvious or whether it's not obvious. What's
Yes.
the question?
Yeah, exactly.
So, but you are saying it's kind of obvious?
No, it's not obvious to me.
Oh, okay, right.
Oh.
Oh, okay. Yeah. So no. Okay. So there is a part that is easy and the part that is very hard. So the part that is easy is the following. Since Clifford operations, just send you from an element of the polygroup to another element of the polygroup.
Yes.
Well, then if you do a Clifford operation, you're just shuffling within the polygroup. So you're just shuffling the weights, but the entropy is the same. Because the stabilizer entropy is the weight that you assign to every element of the polygroup.
Yes.
Okay, so so if your operation is on a pure stay, you do a Clifford operation, the representation, so the state changes, and the representation of the state in terms of the polygroup changes, but you still have the same weights. You don't gain any more, right? Every poly element gets mapped in another poly element, and you are just reshuffling these weights, but then you're summing them. Okay,
Yes.
so this is the easy part. Well, the non-easy part is, what happens if you do transformations that still map pure states in pure states by going to mixed states, so they're conditional operations. Then it gets very tricky to prove it. And there is this paper of Lorenzo Leone and Leonard Bittel that did it. These are a bit of exotic transformations, and that's not easy or intuitive at all. But these are more pathological situations.
Yeah, this was what I was wondering, like whether there's some non-trivial thing hidden, and it's probably this. Then there may be one quick other question. So the whole formalism you have shown is based on the physical degrees of freedom being spins and the operations being Clifford operations, basically. My
Correct.
question is, what about other physical systems? Like if you consider, for instance, bosons, as in quantum optics, like photons, is there something like a stabilizer, formalism, entropy, whatever?
Well, so for starters, there is non-Gaussianity. Non-Gaussianity is a way to assess magic. And then there is an actual bosonic equivalent that but I will leave this question to Salvatore because he's working on that. So I don't know, Salvatore, if do you want to answer right now?
Yeah, so there are different measures of non-Gaussianity in terms of bosonic. So there is, for example, the logarithmic negativity, Wigner negativity, where basically one compute the Wigner function and then compute basically the modulus and compute the logarithm of this function. This is a good measure. It's a strong monotone, has all the possible properties. And recently, we basically understood that it's also measurable, even if something can be quite modified, because one can basically make parity measures to basically get the Wigner function and then as everything. And then there are also the measures that one can introduce that are more based on the fact that one has bosons, or for example fermions. One can always define this kind of measure based on the non-Gaussianity. The principle is always the same. The idea is just to have some kind of observable or object that basically tells you if you are the transformation, if the object is Gaussian or not. That's kind of the point, more or less, for this kind of measure.
So basically, magicness translates to non-Gaussianity, loosely speaking.
Not one-to-one, in the sense that, so for example, for fermions, you have still discrete systems. So for example, you can move between qubits and fermions, because you can just apply a transformation and basically it's the same. And then you can basically observe that you can have transformations that are free Gaussian, but increase the magic, and the opposite, so that increase the magic, but doesn't increase the non-Gaussianity.
I see. Okay. I think there's another question. Thank you, guys.
Hi, Alioscia. Nice. Thanks for the talk. I think it was very comprehensible, even for people like me that don't know anything about magic. From the beginning, I had the impression that magic was something that is the amount of entanglement that you can have that is experimentally accessible. I mean, okay, so
No.
that's why I'm trying to get an intuition a bit more. But so I see the definition that it's a good measure. But when you showed this Bell inequality at the beginning, it seems that if you were to go in a different frame, then you would have access to the magic. Yeah, the maximum access of like quantumness you would go is something that looks magic. So maybe can you correct a bit this picture? Or,
Yeah, so magic and entanglement are two different things. Okay, they have relationships in the sense that, in some sense, they condition each other, but they're really separate. Okay, so you can have entanglement without magic and magic without entanglement. You can have magic only for one qubit, for instance. And magic is how far you are from one of the axes of a reference frame.
Mm-hmm.
So it's relative to a reference frame. Okay. And entanglement per se has nothing to do with where the state is rotating in this reference frame locally, but it has to do with the tensor product structure. Okay, so these are two different notions, and the bottom line is that you need both to have anything that is truly quantum, from violating the CHSH inequalities to quantum advantage or difficulty in quantum simulation.
Right. Yeah, this I understand. So when you say that magic, for example, is in reference to some frame,
Yes.
and maybe I think you mentioned it. So there's the problem of like, what is the relevant frame you should compare to, right? Because you can rotate, and then your operator has like all the entanglement. So,
right.
Is there any advice or intuition, or like, is it understood? Like, what is the relevant reference frame, or that's very system dependent?
No, right. No, so the reference frame is actually fixed by your experimental capabilities. It's really fixed by the fact that you say, this is my qubit. You know, if once you say, oh, this is my qubit, so you know this is your two-level system, this is my z-axis, then there are only two other observables that are maximally compatible with it, and those are x and y, and then you go from there.
Okay, very good. That clarifies many things. Thank you.
No, thank you.
Okay.
Can I ask a real quick question? I'm so sorry.
If
there's no more time, I don't mind it.
Yeah, but we can take questions later after your talk, so he will have the time also to speak, and perhaps something will clarify along the way.
Okay, so should I stop sharing my screen?
Yes. Perfect. Yes, thank you.
Thank you.
So please go ahead.
So hi to everyone. Thanks, qmeets, for this opportunity to talk here. So today I'm going to talk about the result that I did in collaboration with Professor Hamma when I was his PhD student. So the main idea is to try to understand how this magic kind of affects, for example, scrambling, and if we can basically unscramble quantum information. So before to start, let me say that this result is based on 2 papers that I did in collaboration with Lorenzo Leone. That is basically was my co-worker during my PhD, at Lloyd, and Professor Hamma. And okay, so let us start. So why we care about scrambling? This is the first question. So the main thing is that scrambling is basically spreads local information into non-local degrees of freedom. To give a brief picture of what means basically scrambles, we can think to a drop of ink in water. Basically, the idea is that we have something that is really small that is spreading in a large system. And the idea of unscrambling is basically to try to get back this drop of ink from this large pot of water, but just by looking into a small part of the system. That's the point. So this is basically the idea. We want to recover this information, and we question if it's possible. So the main idea is that, of course, we are dealing with quantum mechanics. So in principle, the evolution is unitary. So this means that we should be able to go back and kind of have something that get back to our initial local information. But then the point is that usually we don't have access to the whole system. This means that basically we cannot really use the unitarity of the process, but we have to mock something that is able to kind of reproduce this kind of unitary evolution. So these are the main questions, and this is what we want to try to do. And then the problem is that, of course, there is an hardness related to this task in the sense that we have access to this unitary operator, but then how hard is to reconstruct this information by queries to this unitary operator? And why we care about this is basically black holes are basically considered to be scramblers, because we know that if we send some kind of information inside the black hole, then this one will be scrambled and the output will be the Hawking radiation. And from the Hawking radiation, it's really hard to basically reconstruct the information that we send initially to the black hole. We need some kind of information. But so in this way, scrambling basically offers a way to understand better this kind of black hole dynamics and understand the mechanism of how information propagates inside the black hole and how it comes back. So this is the main question of why we should care about quantum scrambling. So what is the setup? Of course, we can model our black hole in a simple way. We have, for example, the idea of some kind of operator, in this case, Alice, that drop the information inside the black hole. So she's trying to hide or destroy this information. And then we have Bob that instead try to retrieve this information. So one is sending the information about the black hole, and the other one is basically retrieving the information from the output of the black hole. That in this case will be the subsystem. And then, of course, why we cannot access all the information, because, of course, we cannot access the interior of the black hole. That will be C, basically. It's something that we have no access. But then, of course, we need another element. Of course, there is other information that is still spreaded by the black hole, that is this Hawking radiation. So we can think that Bob is looking to the black hole from a long time, and so he has a lot of information about the black hole. And this information is basically given by the subsystem B. So now we want a way in which we have access to D to basically reconstruct this information, and some kind of way to access B to reconstruct this information. So let me first give some information about the scrambling. So as said before, it means that the local information is inaccessible by local output measurements, in the sense that if we look to both system C and D, of course we can retrieve all the information. All the information is stored of A is stored in the systems. But if we look in D, then maybe this information is not inside anymore. Maybe it's all in C, and we want to see if something happens. So a way to quantify this kind of scrambling, it's given by the tripartite mutual information that basically quantify how much of the information of A is in the system of C and D. And the maximum amount of scrambling, of course, has to deal with the size of the subsystem A, and in this case is just -2 log A. And of course, when we have minimal scrambling, it's just when the unitary that we apply is non-entangling, in the sense that, of course, all the information A can be in C, and all the information of B will be in D. And so basically nothing is happening. Okay, so let's go to the main idea. So when it's possible to retrieve this information. So there is this theorem by Hayden and Preskill. It's called decoupling theorem. What is the main idea? So as said before, we have that Bob can just access to the information of D, and somehow we can say that there is some kind of reference system that we can access that basically tells us if everything is going good and we are retrieving this kind of information. So this is maximally entangled with the subsystem A. So all the information that is put in A, we can basically look it in from her. And then we have basically access to just D and B prime, where B prime is basically our prior information on the black hole. What basically they are able to show is that in D B prime, if D is sufficiently large, there is almost all the information about the subsystem A. The intuition that Hayden and Preskill gave was basically of a mirror. Sorry.
Questo va bene, tutto a posto.
There is some kind of interruption.
Svuotata, se no quello è
So, sorry to retrieve. So all the information is stored here just by looking to DP prime. And how we do it. So there is a protocol by Yoshida and Kitaev. The main idea is that we have our black hole. We run some kind of side evolution. We couple these systems, and the idea is that now, while the information was in DP prime, now it's in the C prime and prime systems, but it's all basically the information that we have, and it's basically unscrambled. It's the full information, and we just have to couple them. And the fidelity between the state in output between C prime, R prime, and R is basically our the fidelity that we should look. So now the question is, what happens when we use, for example, a random unitary operator? Then what happens is, of course, that now this object is completely random. So the fidelity will be really low. It will basically be kind of non-existent. But then if we use something that is akin to the unitary operator, so it's the adjoint of the unitary operator, then the fidelity scales like 1 minus 4 over A over the sides of A, 4 over the sides of D. And you see when D is slightly greater of A, we basically have that D scales like 1 minus epsilon. That is basically telling us that we retrieved all the information. But what are the problems of this protocol? Of course, this basically requires that we know the full unitary operator. This means that basically, if we have some kind of black hole, we need a kind of complementary black hole to unscramble this information. And this is not something that we have power of, we don't have this power of computation. So the idea is that if we can kind of lower this kind of expectation, this is one of the questions. So to do it, Professor Hamma before introduced the Clifford group. I will just review really quickly. So the main idea is that we just take tensor product of Pauli matrices. And then we have that the Clifford group basically sends polyoperator into polyoperator. And we can generate the Clifford group by CNOT, Hadamard, and phase gate that we given. But what is the power about Clifford group is that it can be efficiently encoded and simulated. A way to see it is that if we take the polymatrices, we have a simple way to characterize them. We can say that the identity is 0, 0, Z is 0, 1, X is 1, 0, and EY is 1, 1. And this is enough to basically encode all the polyoperator, but then we want to say that also Clifford operator have an efficient encoding, and since basically they map polyoperators into polyoperator, this is pretty easy to see because we can just map the action of the generator of the poly group, and we basically have an encoding for the Clifford group. But then we need also an efficient action. To do it, we can basically look to the generators, Hadamard, phase, and CNOT. So I will give you this practical picture to say how they act on these strings. So you can see that, for example, I can have my strings of X and Z that are basically these two numbers. This will be X and this will be Z. And the Hadamard basically what does is just change the order of these two strings. So as you can see, red goes in blue and blue goes in red. So if I have X, it goes in Z and the opposite. If I have the phase gate, basically, as you can see, what I do is the X component remain the same, but then I do XOR between the Z and the X component. And then with the CNOT gate, instead I have that the XZ component of the controller remain unchanged. but I have XOR for the one on which I'm acting. And in this way, I basically can propagate all these actions, and everything can be done in a polynomial way, efficiently. And this is why the Clifford group is so powerful and can be really used easily. But then what happens, so when we introduce this kind of magic, so when we add non-Clifford resources, so a way to adding non-Clifford resources is basically by adding a gate like the T gate that is non-Clifford. Why? Because we can see while Clifford usually preserves the structure, here as you can see, if we act on a polyoperator, this spreads out in two. And then we can see that if we add more and more T gates, then we will have an exponential spreading after a bit of time. And then first the classical simulation becomes harder, because while at the start we can basically track how they split, so and use all the formulas that I gave you before, then these become harder, become exponentially harder, because then it will increase, and this is a result by Bragg-Costello. Of course, now we can also expect that these kind of resources will affect our kind of learning. So if we think of modeling the black hole or our scrambler like a T-doped Clifford scrambler, so inserting this kind of non-Clifford resources, we can expect that until log n, everything is fine. And then when we go to order r, that is basically exponentially hard, it will become kind of impossible. But then what we found in our work is that there is a region that we call quasi-chaotic, that is in between the classical region where basically everything can be classically simulated, and the one in which there is no hope to do anything, everything is too hard, that is between 2n, whereas between log n and n, where basically we can still do something and can kind of perform tasks that in principle should not be efficient, but still doing it in an efficient way. So now we go basically back to our problem. So now we still question if the Yoshida and Kitaev protocol is the only way to retrieve this kind of scrambled information. What if we add some kind of additional information on our system? And in this case will be that we know that it's a T-doped scrambler. Can we lower the expectation so without any kind of information about the unitary operator? And then we also ask, of course, that the number of queries to the unitary operator are limited, in the sense that we do not expect in a real protocol to have infinite access to a unitary operator. Things change, and also our time is limited. So now we still question if it's possible to unscramble this information. So I will just give you first the result, and then I will introduce basically how they go. So basically what we are able to show is that there is an algorithm that scales polynomially in the number of qubits and exponentially in the number of non-Clifford resources that are added to the system, that has scrambled the information with fidelity that is basically close to 1 as long d is greater than a, d plus t is greater than a, than a plus t. And then the probability, of course, is still affected by the fact that this has to be large. So how it does work? So what is the main idea? The main idea is that, of course, when we are in this region in between the chaotic and classical, we still have some kind of Clifford information inside our system. So there are still some kind of Clifford information that we can use. And this kind of Clifford information is given by the fact that some polyoperator can be still preserved by the action of our unitary operator, meaning that on that specific polyoperator is behaving like a Clifford one. So what is the main idea? The main idea is that we find this set of operator. So this will kind of form a subgroup of the polygroup. And then the idea is to move it in a region that we can basically unscramble through a Clifford operator. This is the main idea. But then we have to find first a way to move this non-Cliffordness, and then still able to decouple the system from the original one. So how we do it? So the main idea is that one can always find a Clifford operator that we move in the case in which, of course, it can be made more general, but in the case in which we have some kind of Clifford operator that is able to split the subsystem D into subsystem E and F, and E is basically the one in which we are able to map all the preserved polyoperator, while F is some kind of trash subsystem in which the information is not well well preserved. And so basically now we have this kind of operator that is able to split it. So it's able to split this one. And I will just give you some intuition how to build it. So the main idea is that we perform some queries on the subsystem D. We learn the poly operators. This can be made kind of efficient. And then we kind of apply some kind of Clifford diagonalization to basically split the system in this way. And this kind of splitting can be made, so if we apply the decoupling theorem to the system, we can basically show that while before it was, all the information was in B prime, as long as E is greater than A minus log A, all the information is now in EP prime. So it's basically a generalization of the decoupling theorem, where now instead of D, we are looking at A. But now the problem is that at the start, we were kind of coupling D to our decoder. So we need something else. And we need to kind of destroy all the information about this threshold system that is F. So we need to forget this kind of information. And the way of doing it is that we know that Clifford are good scramblers, even if are not the best scrambler, they are still scramblers. So the main idea is that while we couple it to our kind of decoder, we kind of trash the information through a random Clifford operator. What will be basically the action is that now we basically enlarged the C prime subsystem, because now we made it bigger. It's like, to give you some kind of intuition, is that like we have our black hole, we kind of enlarged its interior, we kind of forgot about some of the trash information, and we just looked to the part that we knew how to decode the information. And then the final decoder will be the decomposition of this kind of diagonalizer, the one that brings us in the system F.E., then this randomizer, and then back to this diagonalizer to go back to the system D prime. So all these queries can be done polynomially in N, because we are dealing with the Clifford group, and exponentially in the number of T gates that we have in the system, because of course this subsystem F will scale with the size of the number of T gates that we have in our system. So without going too much into detail, what did we learn? So for this kind of quasi-chaotic scramblers, it's possible to move non-Clifford away through Clifford operations. And information about the non-Clifford system can be forgot. So this is also useful if we care about kind of other protocols in learning and dealing with this kind of system. There is always, if we are in this regime, a way to forget about this non-Clifford information and just to care about the Clifford one. Also, it's interesting because basically, if we combine these two, we can extend and we combine it with the decoupling theorem. We can reverse quantum scrambling up to the region in which T is close to N. So still when we have basically some kind of poly operator that is preserved. After that, this kind of protocol doesn't work, but it doesn't mean that it's not possible maybe to do some kind of similar idea. One has to work on it. And then finally, we basically found an algorithm that is able in kind of an efficient way to basically decode this kind of information that in principle required without any previous knowledge on the system and just an exponential time due to the fact that we didn't know anything about the unitary operator. And that's it. Thank you for your attention.
Thank you for the nice talk. I think there were a few questions before, and I hope there will be some also for the Salvatore. So please go ahead.
Yeah, sorry, my question is a bit irrelevant to that talk. No, it's some time ago I was playing a little bit with those measures of non-Gaussianity for bosonic systems for quantum harmonic oscillators, and I needed a similar measure but for fermionic systems. So I was not familiar yet with your stabilizer Renyi entropy work, so I was just playing like that. And trying to define a phase space with Grassmann variables, basically, for fermionic. And actually, the result I got is the same as your stabilizer Rényi entropy, actually. So basically, if you fermionize your system through your favorite Jordan linear, or I mean, you go to a Majorana basis, and the stabilizer Rényi entropy basically boils down to what you would get from a Grassmannian construction of a phase space, basically. So yeah, it was very neat, actually. So yeah, it was more of a comment. But then there is also this construction in terms of a discrete phase space, right? And this theorem that says that the mana basically vanishes for even dimensional quantum systems, right? But it's not the case for the stabilizer.
For odd dimension. At least for the stabilizer is odd dimensional, not even.
I see.
Yes.
Okay, no, it was just to double check, because I was a little bit puzzled by the fact that the stabilizer Rényi entropy does not vanish for qubits. I thought it was an interesting interesting patch to this mana problem. Yeah, that's it.
Okay, is there any other question?
I had a question, but not about distortion. Maybe I wanted to ask Alioscia. Well, maybe I can ask it in general. So I had a question with the stabilizer Rényi entropy for mixed states. What is more rich about it? I imagine both of you can answer that question.
Okay, so you are referring to what I mentioned at the beginning?
Yeah, exactly. Well, because I played a bit with the stabilizer Rényi entropy, and I saw that for certain mixed states it could be larger than for the pure like if you are close to the H state, you can have a slightly larger. But yeah, right. So what is the extra richness then?
Right. Okay. So I'll give you the main idea. Then you should stay tuned, because we're working on it and we're gonna put something out very soon. But the main idea is this. So imagine you have a convex combination, so a probability distribution over stabilizer states. So on the one hand, this stuff does not have magic. Okay?
Yes.
In what sense? What does it mean? Because everything must be operational, right? So what it means is that you cannot distill magic states. So they are useless, right? But now you ask, okay, but who gave you these probabilities, right? You have these probabilities. Who gave you the probabilities? Okay, so, and typically these probabilities are taken for granted. Okay, but one way you can think of this is that if in the world everything is quantum, all probabilities are actually real quantum probabilities. They come from the Born rule. Okay, so you have probabilities because you measured some state and you have these probabilities. And now you ask, is the state that you measured, does it have magic, or it's free? Well, it turns out that it does have magic. So interesting classical probability distribution do need magic in the larger Hilbert space. And the stabilizer entropy for mixed states is counting that, because it will be non-zero generically for convex combination of stabilizer states.
Yes.
But why is this not telling you that you can extract magic from it? It is telling you that it had the cost as a pure state.
Okay.
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 So, well, and then from there you can see that there is very rich structure. But I'll stop here.
Okay, thank you.
So please, one of the two that raised the hand can go ahead.
Please go first, Adrian.
There is also a question in the chat, Adrian. So do you want me to answer the written question, because I saw the hand?
Yeah, sorry, I'm on the train, so I'm not sure if my connection is good enough to ask the question live, but I can still ask it live. I typed it up. Okay, so the quick question was, the map you showed where you had entanglement and magic, it seems that high magic and high entanglement are states that typically are hard or look like are useful for quantum computation tasks. So my question is it known that having both high entanglement and high magic is sufficient for quantum advantage?
Yeah, this is a great question, and I can answer. Okay, so it's necessary. However, definitely it's not sufficient, because one can prove that most states are useless. So, and most states do have high magic and high entanglement. And this is precisely the reason why it's not enough to say, oh, you know, there is a lot of magic and there is entanglement. You need to understand what structure both entanglement and magic have. So, for instance, you know, in the case of entanglement, you don't really care if there is a lot of entanglement. Maybe you care that there is area law. Area law is non-typical. Maybe you care that there is topological corrections to area law. So similarly, for magic, you need more structure than just saying, oh, you know, there is a lot of magic. I hope I answered.
Yes, sure. Thank you very much.
So please, Tori, go ahead.
I have a question regarding something that Salvatore said when answering one of my questions, because now I started thinking again. When it comes to fermions, you said that you can basically transform between fermions and spins. I mean, this is clear. This is the Jordan-Wigner map and so on. But if I look at the stabilized entropy again, fermions still do not have the same Hilbert space than spins, right? Because of the super selection rule. So I'm wondering whether something non-trivial must happen to the stabilizer entropy, right? Because you cannot access basically the full Pauli operators with a single fermion, for instance.
Yeah, no, that's true. That's a good point. In fact, that of course you can basically just restrict yourself on some kind of subsystem. That's true. But the main idea is to consider, like, you have the whole system, you're allowed both kind of transformation, like match-gate, or you're just reducing everything in order to have it. Then you can have transformation that are fermionic, but still and increase, for example, the magic, and the opposite, because one can think, for example, to the match-gate picture, that it's still basically a fermionic way to do computation. There are basically objects that entangle, that are Clifford, that are not in the fermionic subsystems, that are not fermionic operation, and basically will increase the fermionic measure, but will not increase, for example, the stabilizer entropy, or any kind of measure of non-Cliffordness. And the opposite, you can have basically objects that are local, that increase the magic, and still basically that will increase the magic, but will not increase the fermionic quantity. It's something that we are kind of actually looking also. That's why I can say. But the main point is that although one can think to them as unrelated, if one move in the same subsystem, there is some kind of connection at a certain scale in which it's not basically, it cannot be forgotten, this kind of connection. That's something that.
Yeah, this makes sense. Thank you.
So is there any other question for the speakers today?
Oh, I wanted to ask a quick question about the last presentation of Salvatore. So, what differentiates this quasi-chaotic regime from the fully chaotic regime of this T-dop quantum circuit?
So
why is it like n versus 2n?
Okay, so the main idea is that, so in principle, when one has this kind of T-gate, here at least, the main thing is that, so as I shown here, so the T-gate basically destroy one X, but it commutes with Z. So when I'm acting on the circuit, I'm destroying some kind of component, so it will be one, but one of the components will be reserved. So when I insert at least N, so the maximum number of Pauli operator that I will basically destroy is D, but I have still a huge number of generators that I can use that are all at Z. But then after that, I basically destroying everything. I cannot recover the information after that N. And that's the point. Of course, using other circuit. So if I, instead of using T, I use some kind of random unitary, then the thing will be, so it will be slightly lower the number of, so it will not be N, will be some kind of fraction of N because I'm destroying more components. But the main idea is that after that point, I will go there. And then the 2N is given by the fact that I'm reproducing the order of fluctuation of the R measure. Because the main idea is that we assume that chaos is usually connected to random unitary. I have to reproduce that kind of behavior. And when I'm close to 2N, I'm basically reproducing that kind of behavior. That's the problem.
Okay, thank you.
So I think we are at the end. If there is no further question, is there any? Okay, so we thank again the speakers, Alioscia Hamma and Salvatore Oliviero, for the nice talks. And we hope to see you to the next qmeet. So